So basically up till now what you have seen is how to prepare a CAD model, how to tessellate the CAD model, how to convert it into an STL file, and then while you are taking that STL file, how to define the slicing and how to define the orientations. So today what I'm going to discuss is basically the STL file that you create with your CAD model after tessellation. What type of STL file do we get? What are the characteristics of that STL file? And what are the common problems that we encounter in an STL file? So when you look at an STL format, STL is actually defined as stereolithography, and it actually came into being from 3D Systems USA, who developed the first commercially known RP process that is called as stereolithography. So that process was actually developed in 1986, and it used resin as the raw material. And they actually developed this format where a CAD model was actually converted into an STL file for the purpose of storing the data. Now, when you look into an STL file, what you generally find is something like this, where you have three vertices and you have the information of the surface normal. So this is the information of the surface normal, and these are the vertices 1, vertex 2, vertex 1, vertex 2, and vertex 3. So an STL file is basically a set of an unordered list of facets. It's a set of unordered list of basically facets which are triangular in nature, definitely, which represent the outside skin of an object. So it does not reflect anything whether the object is hollow or it is a completely solid or partially solid. It basically reflects the list of facets, and the list of facet is represented in terms of the three vertices. It is the facet basically contains this information, that is vertex 1, vertex 2, vertex 3, and surface normal. So every facet will contain this information, and this information actually reflects the outside skin of the object. Just to give you a brief idea, this is an STL file. So in this STL file, what you will see is that this part actually reflects one facet. This part is actually reflecting one facet. So this is the surface normal. This is the surface normal. And these are the information of the three vertices. And this is the end of facet. So one complete facet has this information stored in the system. So this is the information that is. If you can correlate, what happens basically is that the information is not going to be in a very structured format. It will be a random list. What you need to do in that random list is, if you want to identify which is the edge, like if this is another facet. So what is this edge, this common edge I can find out by identifying the vertices 2 and vertex 3, which will be common for the two facets, so I can sort it out definitely. But initially, in its original form, it is an unordered list. Now when you try to save an STL file, you basically have two formats which you can utilize: ASCII format and a binary format. We all know what is a binary format, and in ASCII format you basically get information in terms of X, Y, and Z. So actually binary format will be more smaller. Have lesser file size, but for human understanding and human reading, ASCII format is more easy. As a result, we save the STL file in ASCII format. And as I explained earlier, each triangular facet is basically described by a set of XYZ coordinate for each of the three vertices. and a unit normal vector with XYZ to indicate which side of the facet is an object. So this is the standard format. This is the standard format of the STL file. Now, what are the advantages of STL file? So the most important advantage is it is a very simple method of representing a CAD model. It generally provides an accurate file of data, which, because all the information regarding the vertices and regarding the surface normal are explicit, they are easy to understand, and they can be easily interpreted. And one of the most important reasons is it is a de facto standard, and most of the RP softwares and RP systems that we have today, they almost use this format for part fabrication. They use this format for part fabrication. So STL has basically developed and grown into a de facto standard for the additive manufacturing industry. Definitely it has a lot of disadvantages also. The main disadvantage that you will find is, although the STL file is larger than the CAD model, only because of the after tessellation, what happens is you have lots of surface patches. Since the surface patches are more, what you observe over there is that you have lot of information. Another side effect of that large information basically is that it sometimes carry many redundant information. It contains many redundant information. Redundant means information that is generally not required or has been falsely included into the data set. And the most important of that is duplicate vertices and edges. Sometimes it creates duplicate vertices and edges because of the tessellation process. During tessellation, what happens is the edges actually move from one location to other. As a result, you get multiple edge information and multiple vertex information. Then there are certain geometrical flaws also in STL file, because most of the tessellation algorithms which are used are not very robust, Even Watson's algorithm, if you start to apply theoretically, Watson's algorithm is considered to be the most robust algorithm during the tessellation process. But when you work on a numerical system, when you work on a numerical object, what you observe is that there are lots and lots of mathematical errors and geometrical errors which creep into the system. As a result, what you basically require is a repair algorithm or a repair software which will actually reduce the production cycle. Because earlier what happened was you had a CAD model, you tessellated it, and then you simply fed it to machine. So this was the system that was conceptualized. But what happened due to tessellation is errors, and errors means rectification. So then it can be fed. So rather than having one single step, now you had two more steps in between, which leads to increase in the production time. Hence, STL file definitely brings in some geometrical errors, and some of those geometrical errors I'll discuss today also. Slicing of the large STL file can take many hours, which is almost undesirable, and that is actually very true. Because what happens in an STL file is that when you have got a large model and a large STL file, and if you are going for a thin slicing, what happens is, because of all the tessellation errors and all the processes that need to be done over here, and then when you feed it to machine, you basically do slicing in between. So this thing basically adds a lot of time. This combination of error rectification and slicing actually takes a lot of time. So before we start, what we have to understand is what is a valid model, because this is something which is very important to know and which is very important to understand. A CAD model is not a valid model. A CAD model is not defined as a valid model. Basically, CAD model is not a complete input. CAD model is actually not a complete input, because if you remember the RP process chain, what happens to the CAD model is tessellation. Now, once tessellation is happening, you are basically breaking this CAD model into smaller surfaces. You are breaking it into smaller surfaces. So when you break it into smaller surfaces, all these information has to be stored and transferred to the next step, which is the process planning, that is layering, then orientation, and then other process planning that are basically needed. So laser scanning part. So this CAD model, you may make a CAD model using any of the software techniques that you have learned up till now. You can use any of the techniques, but this CAD model is actually not the valid input. This tessellated CAD model, the tessellated CAD model is actually the valid input, because this is going to be fed into the system. So when you talk of validity of a model, you are actually talking of a tessellated model. Now, when do we call the tessellated model to be valid? First of all, there has to be no missing facets. There should be no degenerate facets. There should be no overlapping facets, or there should not be any manifold conditions. You already know what is a manifold. We'll discuss in brief in the coming slides. So these are the major problems that you encounter after the tessellation. Either a facet is completely missing, or there is degeneracy. Now, what is degeneracy? Degeneracy is nothing but 3 points which were earlier creating a triangle, now become collinear. That means they cannot form a triangle. They form a straight line. So this problem is called as degeneracy. So what is overlapping facet? So overlapping facet is like there were two triangles which were like this, but suddenly, due to round of error in tessellation, mathematical round of error during tessellation, what has happened is this is one, and this point actually shifted for this over here. So this is like this. So there is a small amount of overlap over here. So the point has actually shifted for one triangle, but it has remained static for the other triangle. So a common vertex has actually been duplicated. So when you have these type of problems, then the model is said to be invalid, and you have to basically rectify these problems using repair softwares or repair algorithms. Now, when a tessellated CAD model is used as an input, it will be sliced into 2D layers. That we all know that what happens, like if this is the model that I'm using, so what will happen is even slices will be cut. So this is the slicing process that has happened. To this. Now, if you look at each slice, what does each slice represent? Each slice actually represents a 2D layer. It is a 2D layer along x-axis and along y-axis, and this is your z-axis. So this is your z-axis. So every tessellated CAD model which is used as an input. So this is a CAD model. And this is a tessellated CAD model. So this CAD model will be sliced, and this sliced CAD model, for each layer, it will look like a 2D layer. Now, once you have a 2D layer, in order to create a 2D layer, what will happen is the deposition will be done like this. The deposition is going to be done like this, which is reflected in this figure. So how this layer is going to be generated? This layer is going to be generated by scanning in one direction of a contour, which will be reflected as a build model, So actually what is happening is a 3D model is converted into 2D contour, which is generated through 1D laying, not layering, laying, L-A-Y-I-N-G, laying. Okay, so that is how a CAD model is defined. Now, once you are depositing in single direction, you have to be aware that all the boundaries have to be there in order to define a valid contour. So solid boundary, what you have read in the solid modeling, the first part, boundary and interior has to be very properly defined. Now, if any of the edges are missing, in that case, it becomes an invalid solid. If any of the edges are missing, it becomes an invalid solid. So once you define a starting and an end point for the layering process, so suppose this is the starting point and this will become the end point. So every hatching that will be done will end at some place. So three basic points. Three-dimensional model is developed as a 2D contour with slices, and each slice is developed as a one-dimensional layering which has a definite boundary and interior points, and there will be one starting point and one ending point according to the geometry of the individual contour, without which the layering process will not be completed. Now, what is an invalid solid? Now, what is an invalid solid? Suppose what happens is you have this cylinder, you have this cylinder, you have this cylinder. Now, what happens is when you are developing this cylinder and when you tessellated it, this is the CAD model, this is your CAD model, and when you tessellated it, you left a gap. There was a gap observed. Now, when I draw the 2D contour of this whole section, what I will find is that this edge is missing. There is a missing edge. You can see there is a missing edge. So what happens when the missing edge is there? So when the missing edge is there, when the layering or one-dimensional hatching that will be happening, what will you observe is that the hatching doesn't stop at the boundary, it ends basically at the end of the table. This is the end of your working table. So this is your working table. So working table end. So when you observe this type of a situation, it basically means that your CAD model is an invalid model for the simple reason that it does not have a boundary. It does not have a defined boundary. So basically now what you need to do is once you observe a gap, you need to repair it. You need to repair it using repairing softwares. You need to repair it using software before you go even further for slicing. So this is the one of the primary examples of an invalid model where the tessellation process, when a CAD model was tessellated, it actually resulted in a gap. And what is a gap? A gap is nothing but a missing facet which needs to be inserted now into the system in order to completely define the solid CAD model. So solid CAD model is not properly defined when after tessellation there are some inaccuracies, mostly gaps. So what are the basic STL problems that you encounter? So the basic STL problems that you encounter is basically these four types. Like there are gaps, as I said, there are gaps, then there is degeneracy, then there are overlappings, and then non-manifold topology conditions. So majorly what you will encounter are first three. Majorly what you will encounter are first three. Non-manifold topology conditions, definitely it occurs sometimes, but it's not very common that you observe non-manifold conditions in a CAD model after tessellation. But sometimes when you have got a very complicated or interlapping surfaces, in that case, there is a chance of non-manifold conditions happening if the tessellation is not robust. So why does these problem appear? First of all, a generic study basically has found that most of these problems are there because of tessellating the trimmed surface. If you have made a model and the model has used trimmed command at places, then tessellation of those trimmed surfaces definitely create these problems. Then where the surface interactions are happening, like if you have one surface like this and there is another surface like this, and then what you have done is you have trimmed it out, trimmed this surface, or rather trimmed this. Using this you have eliminated this. So what happens is sometimes you get these problems very commonly. Then the most common reason for these problems is the numerical errors. Numerical errors. What happens is, for CAD model 5.0000001 and 4.999999 are both equal to 5. Are both equal to 5. So what has happened is, both these points have actually shifted their positions. Have actually shifted their positions. So similarly, if this happens, okay, if this happens, or if this happens, what happens is, this shifts to 5.5 and this shifts to 6. So this shifts to 6. So when this type of problem happens, then you start getting a numerical round of errors, and numerical round of errors will actually, what will they do? They will basically shift the position of the vertices. And once the position of the vertices shift, you start to get degeneracy, you start to get overlapping facets also. So both of these problems actually happen mostly due to either surface intersections and numerical errors. So what are these problems? Let us see in a brief detail. So what is a missing facet or a gap? Okay. When you tessellate a large curvature, basically what happens is, due to all the reasons I have mentioned earlier, because of numerical round off errors, and also because of tessellation of the trimmed or overlapping surfaces, what has happened is, some of the vertices, basically they shift their position, and also due to the overlapping or the intersecting problem, what happens is that some of the surfaces actually get deleted from both the faces. Some of the surfaces get deleted from both the face. As a result, what you obtain is a gap or a hole. What you obtain is a gap or a hole. Now, this is a gap that you observe. So before you move any further, you have to repair this. And how you will repair this? You have to plug this hole. So you have to plug this hole. How you will plug this hole? So what you will do is, you will create a surface manually on this. You will create a surface manually on this, considering surface 1 as your primary surface, and taking vertex V1, V2 and V3 as the necessary vertices. You will create a surface over it. So this is how the missing gaps or the facets are repaired. Now, degeneracy, as I told you, what is degeneracy? A degeneracy occurs when the facet edges are become collinear rather than being distinct. When the facet edges actually become collinear. So when will the edges be, like, if this was the edge, now these three, if it becomes like this, why it has become like this? Because the vertices have actually moved their positions. So what happens is, a geometrical degeneracy of the facet occurs when all the facet edges are collinear, even though their vertices are distinct. Okay, so the vertices still have a unique position, but rather they have changed their location. As a result, what happens is, they have rather become a straight line. So why this generates? This is caused by the stitching algorithm that attempts to avoid shell punctures. So when the tessellation process is happening, so what happens is, the idea of the tessellation process is to create surfaces on every available location. So when that starts to happen, in order to fill the gaps, or in order to avoid any gaps on the surface, what happens is, the vertices are shifted due to numerical errors. As a result, what you get is a degeneracy, where the facets actually become collinear, because the vertices have moved their location. So what will happen is, the resulting facet will be generated. However, this is done at an expense of adding a degenerate facet. The degenerate facet does not contain a valid surface normal. Now, this is a very good pointer or identifier of a degenerate facet. Now, if you look over here, now this is the curve that was there. Now, in order to protect this curve, this has been created. But now, if you look at this shape, or rather this shape also, if you look at this shape also, you see that this is not a triangle. The 3 points have actually become collinear. The 3 points have actually become collinear over here. This is the first point, this is the second point, and this is the third point. Just to fill this gap, these 3 points have become collinear, hence this is called as degeneracy. This is called as a degeneracy. And what is the direct identifier of a degeneracy? The direct identifier of a degeneracy is that the facet that is generated. Now this is the facet that is generated. So this facet will not have a valid surface normal. Okay? That means that they do not represent the topological information about how the surfaces are mated, and this degeneracy has to be removed. So how do you remove degeneracy? You basically, again, you take the surface patch, and you recreate new triangles. You introduce one vertex and you recreate a new triangle. So which will have a valid surface normal. So degenerate facets, if they are generated, will not have a valid surface normal. Now, what is overlapping facets? Now, as I explained, the overlapping facets are generally developed due because of the numerical round-off errors. Which occur during the tessellation process. Because what happens in the tessellation process, in order to fill all the gaps, the vertices sometimes move for different facets. So if these are the vertices which has been generated, now what happens is, for this facet, this vertex remains over here, but for this, it it may shift over here or it may shift over here. So what happens is, you get this triangle. So this is the amount of overlap that is developed on the system. So if you see, this top triangle is actually overlapping on all the triangles which are there in the vicinity. So this is overlapping on all the triangles in the vicinity. So how can you do that? So how can you control this? You can control this basically by defining a tolerance, which is rather set very liberally. So generally what we do is, after the decimal place, we take it to generally like sixth place. We take it generally to sixth place, so as to make a loose tolerance, so that the effect of numerical round off is as low as possible. The effect of rounding off is as low as possible. So there is an option of giving a tolerance for rounding, and the tolerance for rounding is generally kept at the sixth place of decimal, so that the shifting doesn't happen to a very large extent. But there will be some shifting. You cannot completely eliminate all the overlapping facets. You completely cannot ever eliminate all the overlapping faces, because for a large surface there will be hundreds and thousands of facets. You cannot manually, by your own sense, remove all the overlapping facets. But yes, degeneracy has to be removed on all the surfaces and all the curvatures which are available over there. Now let us talk about non-manifold. So you know that there are three non-manifold conditions that you have looked in solid modeling also. So what are the three? A non-manifold edge, a non-manifold point, and a non-manifold face. So generally what we observe is the non-manifold edge condition. This is the non-manifold edge condition, where a single edge is now being shared by how many facets? Four facets. A single edge is being shared by four facets: A, B, C, and D. So that is a non-manifold condition. So in this case, what you need to do is, you have to change the orientation. Basically, you have to change the orientation of these two objects in such a way, or move the location of the joining, so that the edges become distinct. So as we know, a single edge can be shared by only two facets, not by four facets. Then a non-manifold point, like this is the condition of a non-manifold point, where the point is being shared by how many edges? 1, 2, 3, and this surface, So again, this condition generally doesn't happen during CAD modeling, because generally what happens is, either we join the two by either move on a point or move to an edge. When we have two objects which are required to be joined together, we move it either from point to point or edge to edge. So generally when you move it to point, the edge almost inevitably it will come into the picture. So point and face are generally something which are not found very commonly, but definitely edge, it is found in many cases. It is found where the you are trying to create an overlapping surface or overlapping figure, something like this. If you are trying to create something like this, so what generally happens is we create an object like this and then another object, and this is joined with respect to this edge. So when you are joining with respect to this edge, then you have to be very careful what is happening. So rather than joining it like this, we should join through this edge to this edge, so that it doesn't create a multiple facet. It doesn't create a multiple facet. So we have to make sure that one, anyhow, if edge intersection is happening, then the edge is shared by only two facets, not by more, not by four, like in this condition. So as I said, edge and face, edge, this is edge and this is face. So edge and face manifold basically happens very rarely, and that is actually reflected there in the CAD model itself. It is reflected in the CAD model itself because of non-intersecting or non-union surfaces. It will be reflected as a non-union surfaces. So you don't need to bother for that, but definitely edge, you need to be very careful. So this is all about today's lecture.